All right, hypothesis testing. So, pretty much everything we do for the rest of the semester involves hypothesis testing. And that's because hypothesis testing is at the center of making inferences. So, when we do sample comparisons or when we're looking at correlation, there will always be some sort of hypothesis that we're trying to test. And so the simplest version of that is a one sample hypothesis test. So you have one sample of data and you have a hypothesis, and the hypothesis is that the mean of that sample is a particular value. And the alternative hypothesis can be framed in different ways. It can be that the mean is not equal to that value, or that it's greater than that value, or that it's less than that value. And the interpretation of the alternative hypothesis is how you um, evaluate what probability you're looking for. So we'll get to that part uh, later. The main thing is the actual hypothesis, and then the probability that you associate at the end depends on how the alternative hypothesis has been framed. So let's take a look at this particular context here. Uh, we're raising chickens in the backyard, and we are testing this idea that the average chicken will lay 6 eggs per week. So we collect data over a period of 4 weeks. And as you see on the screen, we have a sample of 10 different chickens and how many eggs that they've laid in the 4 week period. So using this data, we can divide by the 4 weeks, take the average, and we find that there's 5.2 eggs per week from the chickens, and the standard deviation is 1.3 eggs per week. So the claim was that there would be 6. We got a little bit less than that. Does that mean that the claim is wrong? Is it actually less? Or is it reasonable that we got 5.2 even if it's true that in general the average chicken will lay 6 eggs? So the claim that we're testing, the null hypothesis, is that the mean value is 6. And then the alternative is that it's not 6. Now we could have said that it's less than 6, but we'd have to have some reason to suspect that it could only be less and it couldn't be more. And right now we don't have that. So right now we're thinking about this as an extreme value relative to 6, but it could be extreme on the other end. So we don't want to negate that possibility or throw out that possibility. So our alternative here is just that it's not equal to 6. So that's the hypothesis test that we're doing. A null hypothesis of 6, of the mean is 6, and an alternative that it's not equal to 6. So if we want to frame this very clearly as a question, how likely is it to get a sample mean as extreme as 5.2 if the true population mean is 6.0? So to get there, we think about the sampling distribution. And remember, the sampling distribution is, you can picture a normal distribution where the mean value is the population mean, and the spread in that distribution is the standard error. So how much from sample to sample we expect there to be variance. Now, in this case, because our sample is small, we're not going to technically use a normal distribution. We're going to use a t-distribution. So remember, when the sample size is small and you're evaluating the mean value, just like we did in confidence intervals, we use the t-distribution. So we calculate the standard error first. So the standard error in the mean, we take our sample standard deviation, which we got from the sample as 1.3. We have a sample size of 10, so divide by square root of 10. Our standard error is 0.41. Then we find the t-score, in this case, the difference between the sample mean and the hypothesized population mean, so 5.2 minus 6.0, and then divide by that standard error. It gives us a t-score of minus 1.95. Now, if we were using the the normal distribution, this would be the z-score, but we're going to use the t-distribution because we're estimating this standard deviation and we have a small sample. So we need to give a little bit more probability for being in those tails of the distribution. Okay. So the t-distribution will look something like this, fairly similar to a normal distribution, but the tails are a little bit wider. The score that we just found out here is minus 1.95. And what we'd like to know is what's the area to the left of this, and that will be our p-value divided by 2. Now, it'll be our p-value divided by 2 because we just are thinking of this as an extreme value, and it could be extreme on the other end as well, right? So we want to find out how likely is it to get a value as extreme as 5.2 eggs, and that could be over here or fewer eggs, or somewhere over here and more eggs. So those would be equally extreme values. So the area over here is that probability that we're looking for, the p-value divided by 2. And we calculate that in Excel using the t-distribution function. So t.dist, put in the t-score that we found. Degrees of freedom in this case is n minus 1. 10 minus 1 gives us 9. And then we always put the value true, so it gives us a cumulative distribution function, which is the left tail probability. And that comes up with a value of 0.041. That's p over 2. Okay. So here what we say is that there's a 4.1% chance of getting a mean of 5.2 eggs per week or less from a sample of 10 random chickens. Our alternative is that it could be less or greater than 6. So we double that 4.1, and that means there's an 8.2% chance of getting a value as extreme as 5.2 eggs per week. Our p-value is 0.082. We're just doubling the 0.041. So that's our p-value. That's sort of the result of the hypothesis test, is finding that p-value, and then you assess what it means. So what does it mean? Well, you have to have a criteria for evaluating the p-value, and that's always established in advance. And very frequently, in many cases, that criteria is that the p-value needs to be less than 5% to reject the null hypothesis. And so alpha is what we name the criteria. Below this value, we say we reject the null hypothesis, and above it, we cannot reject the null hypothesis. So we're clearly 8.2% is bigger than 5%. So we are above the criteria. We cannot reject the null hypothesis based on this data, which means that there's a reasonable chance, an 8.2% chance, that this could have happened if that mean of 6 is actually the truth. If the true population mean is 6 eggs per week, and we get 5.2, that's not an unreasonable result. 8.2% of the time, we'd expect a value that extreme, so like 5.2 or less, or if you're going the other direction, a 6.8 or more. Either of those outcomes is not unreasonable. So we do not reject the null hypothesis here. We find that the null hypothesis is still possibly true.